Hey guys, so today I'm going to be walking you through Chapter 12 for your Math 200 class, which is just about some additional inferential procedures that were not covered earlier in the book. So we're going to start with Section 12.1, which is the goodness of fit test. But first we have to take a look at the characteristics of the chi-squared distribution, because we're going to be using this distribution in this chapter to do some of our inferential procedures. So the first characteristic is that it's not symmetric. The second is that its shape depends on the degrees of freedom, just like the student's t-distribution did. Now, as the number of degrees of freedom increases, it becomes more nearly symmetric. And it's also important to note that the values of chi-squared are non-negative, meaning that they're greater than or equal to 0. So if you take a look at this graphic, you can see that clearly the chi-squared distribution depends on the degrees of freedom, and that as the degrees of freedom increases, it becomes more and more symmetric. Now, a goodness of fit test is an inferential procedure that's used to determine whether a frequency distribution follows some specific distribution. So let's start with expected counts, which is the very first thing that we need to know how to calculate. So let's suppose that there are n independent trials of some experiment, and there are k greater than or equal to 3 mutually exclusive possible outcomes. P1 is going to represent the probability of observing the first outcome, E1 is going to represent the expected count of the first outcome, P2 is going to represent the probability of the second outcome, and E2 is going to represent the expected count of the second outcome, and so on. In order to calculate these expected counts, all we really have to do is take our sample size and multiply it by its corresponding probability for each of the groups. So let's look at an example here. So a sociologist wishes to determine whether the distribution for the number of years caregiving grandparents are responsible for their grandchildren is any different today than it was in 2000. So according to the US Census Bureau, in the year 2000, 22.8% of grandparents have been responsible for their grandkids less than 1 year, 23.9% have been responsible for 1 or 2 years, 17.6% have been responsible for 3 to 4 years, and 35.7% have been responsible for their grandkids for 5 or more years. So this is out of caregiving grandparents, not grandparents in general, but just the ones who are actually the caregivers. So if sociologists randomly select 1,000 of these caregiving grandparents, we want to compute the expected number that we would get in each category, assuming that the distribution hasn't changed since the year 2000. So step one is to go ahead and pull out the probabilities, and these are just based on the previous page. Basically, the probability of selecting a caregiving grandparent who's been caring for the child for less than a year is 0.228. And then 1 to 2 years is 0.239, and so on. These are just from the previous percentages here. Now, since there are 1,000 trials, all we have to do to get our expected counts is take our 1,000, which is our sample size, and multiply by the corresponding probability. So we would expect out of 1,000 actual people to be selected that 228 of them have been caring for their grandchildren for less than 1 year, 239 of them have been caring for 1 to 2 years, 176 for 3 to 4 years, and 357 for 5 or more years. Now again, this is what we would expect based on the data from the 2000 census. So now let's take a look at the test statistic. We're going to come back to those expected counts in just a minute, but let's let OI represent the observed counts of a category, and EI represent the expected counts of a category. K is going to be the number of categories, and N represents the number of independent trials for the experiment. So in order to calculate the chi-squared test statistic, really what we're doing is we're taking our observed values, we're subtracting our expected values, we're squaring those, dividing by the expected, and then summing them all up for I equals 1, 2, 3, all the way to K. Now, this is going to follow a chi-squared distribution with k minus 1 degrees of freedom, provided that a couple of things are true. So all of the expected frequencies have to be greater than or equal to 1. So we can't have any expected frequencies that are less than 1. And then no more than 20% of the expected frequencies can be less than 5, meaning you can't have a lot of categories that all have a very small expected frequency. Now, goodness of fit tests are used to test hypotheses regarding the distribution of a variable based on a single population. If you are looking to compare two or more populations, then what you're looking for is one of the tests for homogeneity presented in section 12.2, which we'll get to in a few minutes. So there are several steps in the goodness of fit test. The first step is to go ahead and determine the null and the alternative hypothesis. And the null hypothesis in this case is going to be that the random variable follows a certain distribution. And typically you're going to have actual values to plug in there. So you wouldn't actually say this. What you would say is that you expect the probabilities to be this, this, and this based on some previous data. Now, the alternative hypothesis is that the random variable does not follow the distribution in the null hypothesis. And this you can just write out in that way, like in those words. Now, step 2, like always, is to decide on a level of significance, which is your alpha value, depending on the seriousness of making a type 1 error. Step 3 would be to calculate the expected counts and verify that the requirements have been met. So we talked about expected counts already. Those are found by taking the sample size and multiplying by the probability in the category under the null hypothesis. So assuming the null hypothesis is true, you're calculating what you would expect to have happen. And then the requirements, again, are that all expected counts have to be at least 1, and no more than 20% can be less than 5. Now, if the requirements of step 3b are not met, which if you look back really quickly, that's you can't have more than 20% of the expected counts that are less than 5. If that's not satisfied, one option that you have would be to combine 2 or more of the low frequency categories into one singular category, and that would work pretty well. Now, if you're doing this by hand, you're going to go ahead and compute your test statistic just by taking the observed values minus the expected, squaring the difference, dividing by the expected, and then summing those all up for every single category. And then what we would do is we'd use table 7 in order to obtain some kind of p-value. Now, this is going to have k minus 1 degrees of freedom, so this is kind of the same way that we look it up when we're looking on our t-distribution. So we're going to be looking at the degrees of freedom and kind of scrolling our way across the table to find the appropriate test statistic. And then we can give bounds on our p-value. Now, step 3 can also be completed using StatCrunch, which I'll show you guys how to do. Now, conclusions should look pretty familiar. So if the p-value is less than alpha, then we decide that we should reject the null hypothesis. If that's not the case, then we fail to reject. And then we go ahead and we state the conclusion in a full sentence. So we're going to look back at this example with our caregiving grandparents. I'm not going to read through this whole thing again, but the basic idea is that in the year 2000, these were the probabilities that that we obtained, okay, the percentages in each of these categories. Now, the sociologist randomly is going to select 1,000 different caregiving grandparents and see if the distribution has changed since 2000. So they went ahead and they collected data from 1,000 people, 1,000 caregiving grandparents, and these were the actual frequencies that they obtained. So these are the actual values. This is what was actually observed. What we expected is something different. This was what was actually observed. So the first thing we want to do is we want to set up our null hypothesis. And we can write the null hypothesis a few different ways. One way is to just kind of express it in words, which would be to say that the distribution for the number of years that caregiving grandparents are responsible for their grandchildren is the same today as it was in 2000, versus the alternative, which is that the distribution is different today than it was in the year 2000. Now, the level of significance that we're going to use is just 0.05. The expected counts we computed in an earlier slide are these values here, and those were based on the probabilities from the year 2000. Now, if you look here, these are the actual observed values, so now we have observed organized next to expected, so we can see exactly where the differences are. So what you can see is that we expected to obtain 228 out of our 1,000 caregiving grandparents who'd been caring for their grandchildren for less than 1 year, but what we actually obtained in our sample was 252. So all of the expected counts are greater than or equal to 5, so there's no issue there, so all of our requirements are met. Now, the test statistic is going to be computed by taking the difference between, and if we take a look back, we have 252 minus 228, so let's see what we're doing there. So we're taking our observed value minus our expected value. So you would take this difference in your calculator and then you would square that, and then you would divide that by the expected value. And then you're doing it for the next category. So you're taking your 255 minus your 239, you're squaring that, and then you're dividing by 239. And you do this for every single category. In this case, there are only 4, so it's not very time consuming. At this point, you might want to go ahead and pause the slide, make sure that you're able to get this answer here. I will show you how to do this in StatCrunch though in just a couple of minutes. So you should end up with a test statistic of something like 6.605. So that should be the value that you get in your calculator when you add up all of these squared differences. So there are 4 different categories, so that means that we have 3 degrees of freedom. So I'm going to minimize the PowerPoint for just a minute and pull up the chi-squared distribution here on my tables. So if I take a look, I want 3 degrees of freedom, so I'm just going to move that to the bottom of my page so I just see 3 degrees of freedom down here. So if I'm looking at 3 degrees of freedom, I'm looking for the value 6.605. Now, chances are it's not going to be actually on my table at all. What I'm going to have to do is look for some kind of bounds. So if you look, 6.605 is between these 2 values right here. So that means that the bounds on my p-value are going to be between 0.10 and 0.05. So I know that my p-value is somewhere between these values. Now, it's not going to be exactly 0.05 because this value is not exactly on my table. So since my p-value is larger than my alpha, I'm going to fail to reject the null hypothesis. And we'll go ahead and conclude that there is not sufficient evidence to conclude that the distribution for the number of years caregiving grandparents are responsible for their grandchildren is any different today than it was in the year 2000 at the 0.05 level of significance. So basically, even though our expected and our observed counts weren't exact, when we looked at the differences between the two and calculated the test statistic, there wasn't enough evidence to suggest that the proportions are any different today than they were in the year 2000. Now, I want to show you how to do this in StatCrunch as well. It's very easy. So this is the goodness of fit test. So really what I'm going to do, if you look over here, I have, let me make this a little wider so we can see it. We have the number of years, and I apologize, some of these are formatted as dates because I put them in like as 1 to 2 years. So this should really be 1 to 2 years, and this was 3 to 4 years. Now, if you look here, I have the observed counts and I have the expected counts. So all of this is already typed in. So now what I'm going to do is I'm going to go to Stat, Goodness of Fit, chi-square test, and then I select my observed counts in this place right here, expected. I select right there. If all of the cells are expected in equal proportion, then you could click this little bubble right here, meaning if all of your expected counts were exactly the same. And then I just do compute here, and gotta scoop my stuff over. Let's see here. So 6.605, that's what we got for our chi-squared value as well. And if we look back just one slide here, we knew that our p-value was somewhere between 0.10 and 0.05. This gives us an exact p-value, 0.0856. It's still rounded, obviously, but it's more exact than we're able to get on our actual table. So that's under Stat, Goodness of Fit, and then chi-squared test. Okay, so let's take a look at section 12.2 now, which goes through 2 different tests, the test for independence and the test for the homogeneity of proportions. So the chi-squared test for independence is the first thing that we're going to go through, and that's used to determine whether there is an association between row variable and a column variable in a contingency table constructed from some kind of sample data. So the null hypothesis in this case is going to be that the variables are not associated, meaning that they're independent, and the alternative hypothesis is going to be that the variables are associated, or you could call them dependent. So in a chi-squared test, you're always going to have a null and an alternative hypothesis that look just like this. So the null hypothesis is going to be that the variables are independent. The alternative is going to be that the variables are not independent. So, the idea behind testing these types of claims is really to compare actual counts to the counts that we would expect if the null hypothesis was actually true, meaning that if the variables were actually independent, what would we expect? Now, if a significant difference between the actual counts and the expected counts exists, then we would take that as evidence against the null hypothesis. Now, in order to compute the expected frequencies in a certain cell, all you really need to do is you need to multiply the row total by the column total and divide by the table total. Now, this I'm going to show you how to do by hand. It's not very difficult at all. It's just multiplying and dividing. But you can also get these values in StatCrunch, so I'll show you that when we get to it too. So let's take a look at this example here. So in a poll of 883 males and 893 females, they were asked, if you could have only one of the following, which would you pick? Money, health, or love? So their responses are presented in the table below, and we want to determine the expected counts within each cell if gender and response were actually independent. So really what we're doing is we're using the multiplication rule of independence in order to calculate our probabilities. So the first thing you want to do is you want to put this, and this is if you're doing it by hand. Again, I'll show you guys how to do it in StatCrunch in a couple of minutes. But first thing you're going to do is you're going to just arrange this so that you have row totals and you have column totals as well. And then you also have a table total. So this is just the sum of these two. This is just the sum of these three, and so on. And then what you do is you take, for example, if we're interested in this one right here, the men who said that they would value money, you take the column total, which is 128, multiply it by the row total, which is 883, and then you divide by the table total of 1776. For example, with women who chose money, we would take 128, which is your column total, times 893, which is your row total, and divide by 1776. So that's going to give you expected counts in each place. So we would expect 63.64 men to answer money, 507.13 men to answer health, and so on. Now, in order to actually conduct the chi-square test for independence, we have to calculate a test statistic, and you'll notice this looks exactly the same as it did before. This is going to follow the chi-square distribution, though, with a different number of degrees of freedom. So since we have rows and columns, what we're going to do is we're going to take the number of rows and subtract 1 from that. We're going to take the number of columns, subtract 1 from that, and then we multiply the two in order to get the degrees of freedom. Now, a couple of things have to be true. Those same sort of conditions need to be met. All expected frequencies have to be greater than or equal to 1, and no more than 20% of the expected frequencies can be less than 5. So let's go through the steps, and then we're going to go back to that example. So in order to test the association or the independence of two variables in a contingency table, we use the following steps. The first step is to determine the null and the alternative hypothesis. The null hypothesis is that the row and column variables are independent, and the alternative is that they are dependent or not independent. And then you choose a level of significance alpha. You calculate the expected frequencies and verify that the requirements are met. And then you compute the test statistic and use the table in order to calculate the p-value. So most of this should look exactly like the stuff from from section 1, just has a different number of degrees of freedom. And we can also do this in StatCrunch, and then we can use our p-value and everything else in order to state a conclusion and figure out what we should say. So let's take a look back at this example. So in a poll of 883 males and 893 females, we obtained the following results. Okay, so 82 men said that they would choose money if they had to pick one between money, health, and love, and so on. So what we're trying to test is the claim that gender and response to this question are independent, and we're doing this at the 0.05 level. So our null hypothesis is going to be that gender and question response are independent, and the alternative hypothesis is that gender and response are dependent. Now the level of significance in this case is just 0.05. So the expected frequencies were computed in the previous example, okay, and those are given in the parentheses here. The observed frequencies are actually what we obtained. Now, observed frequencies are always going to be whole numbers because we're actually observing this happen. So we actually had 82 men who answered the question money. We had 446 men who answered the question with health. We would have expected 507. That's what this is saying. So none of the expected frequencies are less than 5, so the requirements are met. So if we calculate our test statistic, we're going to do this the exact same way that we did before, which would be to take our observed, subtract our expected, square the difference, and then divide by the expected for each of the categories, and then we add it all up. Now, what you might want to do is you might want to pause it while I have it on the screen right here and go ahead and try to calculate that test statistic. This one's a little more tedious because we have 6 groups instead of just 4, so you're going to have a little more to do in your calculator. But again, I'm going to show you how to do this in StatCrunch. It can be a little tedious by hand, particularly if you have more groups than this. So you should get a chi-squared test statistic of 36.82. Now, we know that there are 2 rows, male and female, and 3 columns, which are the 3 choices to the question. So in order to calculate degrees of freedom, we take 2 minus 1 and we would get 1, and we take 3 minus 1 and we get 2, and we're just taking the product of those 2. So 1 times 2 gives us 2 degrees of freedom. So again, if I pull up my table, so let me minimize this and pull that up, I'm going to look at 2 degrees of freedom, and I know that my chi-squared test statistic was very large. It was 36.82. So if I look at 2 degrees of freedom and I scroll my way across, 10 is the largest value I have. So 36 is way off of my table, okay? So it's going to be approximately 0. Now, since the p-value is going to be smaller than the alpha value, we're going to go ahead and decide to reject the null hypothesis. So we would say that there is sufficient evidence to conclude that gender and response are dependent at the 0.05 level. Now, we can also do this in StatCrunch, and this is one of the trickier things to do in StatCrunch, so I want you to pay really close attention here. So let me pull this off to the side so you guys can see how the instructions will be helpful. Let me minimize my table and done with that. Okay, so I'm going to just scroll over a little bit because I have the data entered right here. I have men and women, that's under the gender category here, and then I have money, health, and love. So these are the number of people who answered with each of these responses. So I'm going to go to Stat, Tables, Contingency, and then I'm going to have to scroll over because it's not letting me do that. Okay, and then I have summary data, so I do with summary, and this is where it's a little bit tricky. So what you need to do is you need to select all of the columns that are in this case, the answers to the questions. So the 3 different categories are the money, the health, and the love. So in order to select those all at once, what you're going to want to do is click on the one that you want and then hold down and do shift and select all of the categories that you're looking for. So in this case, we're basically just selecting the categories that have the actual counts in them, which in this case are the money, the health, and the love category. Now we have labels, and those are our gender labels, either male or female. And again, the rows, those are not, the row labels should not have actual numbers in it. They should just be the category names. These columns right here that you select, those should be where the actual data lives. And then I want to select a couple of other things. So I want to select contribution to chi-squared and expected count here. And if you look, I want the chi-squared test for independence, which is already selected, so I just do compute. And I'm going to have to scoot it over a little bit here. But what you'll see is that we get a value that's very close to the value we calculated on the previous slide, 36.8. P-value very, very small. It says less than 0.0001. Okay, so it's really tiny. Now, a couple of things you can see here. I had mentioned that you could calculate expected counts in StatCrunch. This is exactly how you would do it. So we observed 82 men who answered money in response to the question. And what we would expect, this is kind of like a little legend here. So the first number that you see in any of the cells is the count. The next number that you see, which is in parentheses, is the expected count. So that's going to be this value right here. So we expected 63.64. And then this last value that I had it display was the contribution to the chi-squared. So this tells you my chi-squared statistic is 36.8. And we can look and see where the largest contribution was to our chi-squared. So if you look, we have 5.3, 7.37, 5.86, and so on. The largest contribution is the 7.37. And if we look at this, this is men who answered health. So we would have expected 507 men to actually say that they would value health the most, but only 446 men actually did. So there was kind of an inordinately small number of men who actually answered health based on what we would expect to have happen. So that was the largest contribution to our chi-squared. Okay, last test is the test for the homogeneity of proportions. So in a chi-square test for homogeneity proportions, we test whether different populations have the same proportion of individuals with some characteristic. Now, the procedures for performing this test are actually just completely identical to the test for independence. So I'm going to just rely on technology to show you guys how this one works. But let's look at this example here. So we have a question that was asked of a random sample of individuals in 3 different years. It was asked in 1992, 2002, and then in 2008. And the question was, would you tell me if you feel being a teacher is an occupation of very great prestige? So they could either answer just yes or no. And if you look at the results in 1992, out of it looks like there were 1,020 people asked. 418 said yes, 602 said no. And then you can see that the yes category is growing a little bit over time. It becomes the majority in 2008. So we're going to test the claim that the proportion of individuals that feel being a teacher is an occupation of very great prestige is the same for each of the years. So our null hypothesis would be that the first proportion is equal to the second proportion is equal to the third proportion. And the alternative is that at least one of these is somehow different. So we're not necessarily figuring out which one, we're just saying that at least one of them is different. Our level of significance in this case is going to just be 0.01. So we're going to use technology for this. So let me minimize this. And let's see. Make this a little smaller too. And I'm going to scroll over, close out of that. And if you look here, I have the question response, either yes or no, and then I have the 3 different years that the question was actually asked. So this is our data over here that we're going to be using. So if we recall from the previous demonstration, I do stat, tables, contingency, and then I want with summary, because my data is already in a summary table. Now this again, I have to select more than one column. So I select anything that actually has data in it. So that's going to be 1992 all the way to 2008. So again, on my keyboard, I'm clicking on the first one and then I'm holding down Shift and selecting the last one, and it highlights all of them at once. Now my row labels are just my yes, no, my question responses. And then I want to go ahead and select a couple of things. Let's do the expected counts again and the contributions to the chi-squared. And we just leave this where it is and we do compute. And what you'll see is that we end up with a chi-squared statistic of 24.7, which corresponds to a p-value that's very, very small. So if I just go back here for a minute, I can go ahead and decide that I should reject the null hypothesis, and I would say that there is sufficient evidence at the 0.01 level to conclude that the proportion of individuals who believe that teaching is a very prestigious career is different for at least one of the 3 years. And if we look at our contributions to our chi-squared value, we have some kind of large contributions. 6.97 over here and the 6.22 are the largest contributions. And this one, if we look, in 1992, we would have expected 475 people to say that yes, teaching was a prestigious career, but only 418 actually did. So in 1992, it wasn't believed, I guess, that teaching was a very prestigious career. But in 2008, we would have only expected 471-ish people to say it, when really 525 agreed with the statement. So we can tell that there is some kind of shift that's happening, and we can conclude that the proportion of individuals who believe that teaching is a prestigious career is different for at least one of the 3 years. So that is really it. I would highly recommend that you utilize all technology for these particular tests in Chapter 12, just because they can be very time consuming and easy to mess up if you do them by hand. But that is it for this week.